This is Dr. Muhammad, and this is another course which is Mechanics of Materials. And today we are going to talk about an introduction about this course, and I hope that we can get a good introduction regarding mechanics of materials and the basic definitions and the important definitions for it. Okay, so let's go directly to the contents. So first of all, as you can see here, we are going to discuss today different items. First of all, we're going to highlight or give an exposure about the definition, basic definition for mechanics of materials. And after that, I'm going to give some insights regarding the objective of mechanics of materials. And after that, I'm going to talk about the need of mechanics of materials in general, why we need it, what is the main reason, and what are the important aspects where that we need mechanics of materials. And then I'm going to talk about the theoretical analysis versus experimental results approaches, two different approaches we're going to have whenever we are talking about mechanics of material in general. We are going to have theoretical analysis and experimental results and how they are complement one another in order to let us know more about mechanics of materials. And then I'm going to give a little historical background talking about who were the pioneers of this field and when exactly it started, and who were the leaders for or in the field of mechanics of materials. Okay, now let's go directly to the definition. Let's go directly to the definition of it. So first of all, we can say mechanics of materials is a branch of applied mechanics. So we can say that it is a branch of applied mechanics that deals with the behavior of solid bodies. So we're talking, the subject here is, or the main item that we are going to work on is solid bodies subjected to various types of loading. Okay, so this is considered to be the definition. Okay, it is a branch of applied mechanics that deals with behavior. Again, this is important point here, which is the behavior of solid bodies. So we're not talking about liquids, for example, or gaseous materials or gas or something like this. We're talking about solid bodies subjected to various types of loading condition, whether that it is like if we are having compression, or if we have tension, or if we are going to have torsion, or we are going to have bending, as we are going to see. Okay. And then other names for this field of study are, so we have different names here. Let's clear everything. So there are other names related to mechanics of materials, which is the strength of materials. This is another name, common name that you're going to see also, and you're going to find it is commonly used in the scientific fields. And mechanics of deformable bodies. This is a third name, or we can say a second name after mechanics of materials and strength of materials and mechanics of deformable bodies. Some people, they like to call it structure mechanics. Also are going to find some people calling it structure mechanics. Maybe that the title itself is not very giving the right description, but anyway, some people, they like to use this title. And after that, the solid bodies include, what is the type of solid bodies that we have mentioned here? So the solid bodies include bars with axial loads. So we are going to have bars. Whenever we have bars, for example, okay, that is going to be under axial load with our tension, for example, or compression. So this is considered to be something similar to or some of the solid bodies that is going to experience some stresses related to the axial forces. shafts in tension, for example, and beams in bending. So shafts in torsion, as you can see here, this is a shaft, which is commonly it is like fixed at one end, and then it is going to be subjected to torsion, okay, or like moment in this direction, for example, that is going to make this solid body or this shaft to experience torsional stresses. Or we are going to have beams. Okay, so beams means that we're going to have a solid body that is supported at the ends, as you can see, and due to concentrated loads we are going to find that it bends. This bending would make this solid body to experience some tensile stresses at the bottom and compressive stresses at the top, and in between there is kind of gradual change between the tensile and compressive stresses. And we are going to deal with columns in compression as well. So we are going to have columns, as you can see here. This is a column, okay, and we are having concentrated load. Commonly it is going to be under compression. So this is the case of the compression or axial load. So whenever that we are dealing about stresses and strains, we need to know that how the material or the behavior of the material. So that's we can say this is what the definition is all about. Okay, so we are going to see how the behavior of the material is going to be changed. For example, in this figure, you can see that we have stresses in the vertical axis, strains in the horizontal axis. If we're talking about steel, for example, we're going to find that for steel specimen under tensile forces, we're going to find that the behavior of it is going to be something similar to what you are going to see here. And we can, whenever that we understand the behavior, whenever that we say that this part is elastic, this part is yielding, this part is strain hardening, this part is nicking, so we are going to have kind of more understanding and a thorough understanding of the behavior of the material itself, so that it will help us in the design of whatever elements and components composed of this material, and it is going to provide us information about how this material or how this component or this element, which is a solid body, going to behave under different phases of loading. So this is very important regarding the definition. Okay, now let's go to the next part, which is related to the objective of mechanics of material. Before we have understood what is the definition, now what is the objective of it? The principal objective of mechanics of materials is to determine stresses and strains. So let's go back here and see. This is the curve that we are going to have commonly, and we are going to find that stresses here on the vertical axis and strains are going to be here. And as you can see, that this is the main or the major or the main principle that we want to know, this stress strain curve. This is the major thing for us. Okay, so the principal objective is to determine stresses and strains and displacements in structures and their components due to the loads acting on them. So we are having like 1, 2, 3. We have 3 things here. Something related to stresses. I'm going to talk about stresses later on, whenever that we have solid body and there is load is being applied on it. So if we have a cross-sectional area here, let's assume it's A. So the stress is going to be, as we're going to see, it is P over area. This is the meaning of the word stress here. And strain, it means that under this tensile forces that is being applied on the system, the original length of the solid body is going to be extended, as you can see here. It is going to be extended. Okay, so this length, extra length, okay, we call it delta, for example. So after being applied, or the force being applied, then we're going to find that the length of the element is going to be L plus delta. Okay, So this delta is what we are talking, or this is this delta is the extra length that is over the original length after the solid body deformed. Okay, and this strain is going to be like the extra length that is going to be developed because of the load application over the length of the original solid body, for example. This is what we call it the strain, and I'm going to talk about it in detail later. And the last thing is the displacements, which is already, this is delta that I have mentioned before. Let's clear here. Okay, so anyway, we are interested in these things, basically stresses and strains. Okay, and then displacements, we're going to think about them. Okay, so this is the stresses, strains, and displacements. If we can find these quantities for all values of the loads up to the loads that cause failure, take care of this word, failure. This is very important word whenever that we're talking about mechanics of material. Why? Because failure, if I go back here, look here, this is the fracture stress, for example, the point where that the material is going to fracture, failure, there is a failure here. Okay, failure if we're talking about something, or tensile, for example, we are having like nicking here, for example. Okay, so this is, after that there is failure if we're talking about tensile stresses. So we are very interested in this because this is very dangerous for our structures in general. So we need to know when and where this failure is going to take place, right? Okay, so this is the word that we need to take care of. We will have a complete picture of the mechanical behavior of these structure. That's right. If we know how and when this element is going to fail, then we are going to have a complete picture, full understanding. Okay, so if we could understand the stresses, okay, if we could understand what is the strains and the additional displacements that is going to take place, and we are having a full understanding of what is the behavior of the material under different types or under different phases of the load, then we are going to find that our stress strain, so we're going to find and say that, well, our material is going to fail here at this specific strain and at this specific stress after certain like elongation or after certain or specific displacement that can be attained by the element itself. Okay, now let's go to the next part, which is the need of mechanics of material. So this is the need, why we need it. So an understanding of mechanical behavior is essential for the safe design of all types of structure. This is the key word here, safe. So we need it because we want to design safe structures. Whether these structures are airplanes, antennas, buildings and bridges, machines and motors, or ships and spacecrafts. Okay, so they are important. You're going to find mechanics of material in every field, almost every field, because they are important for the safety of the design of the elements and structures that we are dealing with. This is why mechanics of material is a basic subject in so many engineering fields, and this is right. Here, this is, as you can see here, an aircraft. You're going to find something very, very small here, which is the landing gear strut. Okay, landing gear strut, that whenever that we have the wheels here and they're connected and there is a strut here. This strut is under, actually it's under compression. So we are going to design this strut to receive loading from the aircraft, and we are going to look to what we call it the stress strain curve, for example, for it. And we are going to design this landing gear strut based on structural mechanics or the mechanics of materials rules or laws in general. Okay, so that we are going to have a safe design. This strut should not fail under the load coming from the aircraft. In a similar fashion, we can look to this, the tow bar here. This tow bar is under tension. So if there is small car here, okay, is like towing this aircraft, so this tow bar is going to be under tension. We need to design it to be safe and not exceeding the limit state that we are designing for. Okay, so this means that mechanics of materials is very important branch of science that we need to take care of, and this is actually the main subject of our course for our course. Okay. Okay. Another thing important for the needs and also differentiating between the mechanics of materials and statics and dynamics. So statics and dynamics are also essential. Okay. Because I think that most of you already have studied statics and dynamics before. But those subjects deal primarily with forces and motions. That's important. Whenever that we have elements, these elements are going, for example, if we're talking about building structures, for example, and there is like lateral load coming from earthquakes or wind. So we're going to analyze the building in order to know what are the forces inside that is going to be developed inside the building or inside the structure skeleton. This is based on the forces and analysis of forces. This is related to statics. If we're talking about dynamics, then if we have an earthquake, for example, then the dynamics of the structure should be studied well in order to know how much forces are going to be imparted or going to be induced inside the structure that we are studying. Okay, and then based on the analysis, dynamic analysis, we are going to tell what are the shearing force here, what is the bending moment there, what is the displacement, lateral displacement here. So that's the issue. So we are stopping at these fields with forces and motions associated with particles and rigid bodies. However, in mechanics of materials, we go one step further by examining the stresses and strains inside real bodies. So we're going to study something that is, as we said, we are going to one step further. So we're going to talk about stresses and strains. Do you remember? So this is the famous curve that we are going to have always, stress-strain curve. Okay, for whatever the material that we are going to have. So we need to know what are these stress and strain curve for the material or for this element in order to know whether that we are in the safe side, we are reaching failure or not. So when these stresses and strains, especially stresses, they are forces over the area. So we are going to obtain forces from statics or dynamics, and then we are going to one step further by checking the stresses based on the rules that we have. Okay, so let's clear everything here. To determine the stresses and strains, we use the physical properties of the materials as well as numerous theoretical laws and concepts. So we have like physical properties, we need to think about them and we need to know well them regarding the element under investigation. So we need to know the physical properties of the materials as well as numerous theoretical laws and concepts. We need to know a lot of theoretical laws and concepts as we are going to see during the course. So don't worry, we are going to find a lot of theoretical laws and concepts need to be applied. Okay, now this is the need for mathematical or for the mechanics of material. Now let's go to the theoretical analyses and experimental results and what is the difference between the two and when we need this and when we need the other. Theoretical analyses and experimental results have equally important roles in mechanics of material. This is very true, I think. We use theories to derive formulas and equations for predicting mechanical behavior, but these expressions cannot be used in practical design unless the physical properties of the materials are known. So you can see here, we need to use theories, okay, which is theoretical analysis, equations and so on, to derive formulas and equations. That's very nice, okay, but they are highly dependent on the physical properties of the materials, okay. Physical properties needs experiments, okay. Such properties are available only after careful experiments have been carried out in the laboratory, okay. This is the main thing that we need to put in our mind, okay. Such properties are available only after careful experiments have been carried out in the laboratory. Not all practical problems are amenable to theoretical analysis alone, and in such cases physical testing is a necessity. Of course, sometimes physical testing is a necessity, or it's necessary to make the physical testing for the material in order to understand its behavior. Okay. Now let's go to the last part of this lecture, which is related to the historical development and of mechanics of material. The historical development of mechanics of material is a fascinating blend of both theory and experiment. Theory, okay, between theory and experiment, actually, both of them, they are complementing one another. Theory has pointed the way to useful results in some instances, and experiment has done so in others. Okay, so they are, as I said, complementing one another. One of the early pioneers in this field is considered to be, or we can say that he is like the father of mechanics of materials. Actually, in 1452 and to 1519, Leonardo da Vinci, he lived between these. This is Leonardo da Vinci, as you can see him here. He lived between 1452 to 1519. Okay, and Galilei lived between 1564 and 1642. This is Galileo, as you can see him here. Okay, they performed experiments. Look here, experiments. So they used experiments here to determine the strengths of wires, bars, and beams. Okay, wires. Okay, which is wires means that it is only under tension. Bars, that is commonly under compression or maybe also under tension, and beams, which is like bending, for example, for bending, if we have beam and we have forces here. So they performed experiments on this. Although they did not develop adequate theories by today's standards to explain their test results. Actually, they didn't provide the adequate theories for whatever they have done, but they are considered to be first people, okay, and they considered to be the pioneers in this field, Leonardo da Vinci and Galileo Galilei. And the last one that is actually, he is prominent one in this field, is the famous mathematician Leonhard Euler, as you can see him. This is Leonhard Euler. Not sure, this is actually the picture that I found, so I'm not sure whether that is, but I think that commonly this is the person. Okay, he lived between, in the 18th century, between 1707 to 1783. Developed the mathematical theory of columns. That's very important. If you go to the course of indeterminate class, you are going to find, or also for steel, in the beginning of steel structure, I was giving some introduction about the historical background, especially for columns. Whenever we talk about columns and Euler buckling load, you are going to find Euler as being mentioned many times. So the theory of columns and calculated, he is considered to be the developer of the mathematical theory of columns and calculated the critical load of column. We call it Euler load buckling in 1744, long before any experimental evidence existed to show the significance of his results. And you can imagine that without appropriate tests to back up his theories, Euler's results remained unused for over 100 years. Can you imagine? For 100 years it was not used. His theory wasn't in use, although today they are the basis for the design and analysis of most columns, and this is very true, very, very right. So I think that we owe him a lot regarding the mechanics of material. Thank you for listening, and this is I hope this introduction, this little introduction, is going to provide you with the main and basic concepts. Let's recap what we have mentioned here in today's lecture. I have touched upon main 5 points. I give some definition for mechanics of material, and we said that it's a branch of applied mechanics. And we mentioned about the main objective of mechanics of material, and we said that we need, or we are objecting, or we have, the main objective is stresses, strains, and displacement. After that, we mentioned about the need of mechanics of materials, and I mentioned about the importance of designing safe structure based on knowing the behavior of them in stress and strain at different phases, especially at the failure phase. And then I talked about theoretical analyses versus experimental results and which one is more important, and we concluded that both of them are important and complementing one another. And the last item was related to historical background. We mentioned about Leonardo da Vinci, Galileo Galilei, and Leonhard Euler. They were pioneers and they contributed a lot to the starting of this field of science or mechanics of material. Thank you for listening, and see you in the next lecture.